During a recent 12-month period, over 1,000 research sounding rockets were launched, principally from the North American continent. With so many satellites in orbit, why does the United States launch so many sounding rockets? For one thing, the relatively low cost. For another, the ability to carry relatively large payloads. The ease and low cost of payload recovery. The checkout of experiments which may be later flown in satellites. In this chart of the atmosphere cross-section, you can see the gap between balloons and satellites. Sounding rockets fill this gap, contributing to the world's scientific knowledge about weather and the ionosphere. At NASA Wallops Station on the Atlantic Ocean in Virginia, we can examine some of the facilities to guide the establishment of a new rocket research range. Procedures shown in this film have been modified from U.S. operations to fit the capabilities of a newly established range. What are the requirements of such a site? Obviously, the more room available, the better. And any plan should provide for expansion if possible. A research range tends to be shaped as a sector, as wide as practical. The size and angle depend greatly on the population density and safety considerations. Locating a firing point on a shoreline usually makes the impact area easier to clear. However, with land ranges, recovery of payloads is easier. Recovery of experiments brings back sample data, such as particles, camera film, or emulsion packages, and may permit reuse of the scientific instruments. The search for a launch site should take you as far from populated areas as possible and still get access roads, communications, water, and electrical power. Consider the number of people, perhaps 25, who will require living space, and the conditions of their habitations, temporary or permanent. Having selected the site, let us look at the requirements of a launch facility, considering that each nation has its own special problems, experiments, and boosters, which may require modifications in this hypothetical plan. Let's look first at the rocket storage areas, located at least a half-kilometer from any area where people will normally live or work. Ready storage may take this form, in a remote building. Farther, too, if there's no barricade. Control the access of people to this area and avoid the possibility of fire. Each rocket is electrically grounded, and the building itself is grounded to a well-buried girdle of copper wire or strip. Sometimes boosters are stored in open sheds, awaiting preparation for use. A separate building is usually needed for handling the payload, especially if pyrotechnics or explosive grenades are to be handled. Depending on the payload requirements, this area is at least 10 meters square and located with access to the rocket assembly building. Here we see electrical checkout equipment and handling systems provided depending on the nature of the payload. For example, for the grenade experiment, the timer is checked with a system of telltale lights. This test answers the question, does the timer deliver firing pulses at the proper instant and in the planned sequence? Provision is made for tools required in rocket and payload assembly, and sufficient spare parts as required. If the checkout shows a weak component, it must be replaced, or the repairs may delay the firing. Many launch facilities include buildings which contain the telemetry equipment, tracking equipment, and data recording. Sometimes these are in vans, or sometimes in the blockhouse. Telemetry is monitored during calibration and checkout. Telemetry during the flight is received, recorded, and displayed. Workspace and test facilities should be provided to perform pre-flight assembly and electrical checkout of instruments. Tracking equipments may be remotely located, such as this GMD-1 tracker, or a radar such as SCR-584. Indications from such equipment are relayed to the instrumentation facility. Sometimes van mounting of instrumentation gives flexibility in experimenting and permits the return of expensive equipment to the base laboratory for calibration and testing during inactive periods of the range. Ground support items are as important as the rockets and their payloads. Weather data correlates ground observations with sounding rocket observation and also determines the ability to launch. Wind data and wind shear information are particularly important in the launching of simple research rockets, which in some cases are quite sensitive to winds. Locate the launch pad a safe distance from any other facility, depending on the rockets, with a clear flight path to the range area. The launch pad is at least 15 meters square. It is provided with floodlights, loudspeakers, and telephone. Sometimes pad cameras observe the launch and document the activities. Other cameras on remote sites may observe test phenomena. The launchers are usually simple rail types, selected to match the type of rocket. Elevation and azimuth are adjustable, as changes in wind conditions often require changes in settings, even as the firing time approaches. The control center is located so that underground power and communications cables can be run to the launch pad. Sometimes referred to as the blockhouse, this may also contain the instrumentation. Obviously, this building has the heaviest roof and wall construction of concrete or cinder blocks. Windows, if provided, must be thick, 10 centimeters or more. Instead of windows, some facilities use closed-circuit television equipment to permit close observation with personnel safety. Provided technicians are available for maintenance, cost of this equipment is relatively low. Multiple TV cameras provide varying viewpoints, usually with pictures clearer than shown in this motion picture film. Simple radar is used to track the payload. Sometimes these radars also observe the area for range safety. Radar data is photo-recorded for analysis of trajectory. Precision oscillators provide time code generation, feeding a series of accurate pulses to recorders, cameras, and other instrumentation. Often, remote sites are used for cameras or tracking. These require timing signals and communication by landlines or radio. Storage, assembly, communications, control, timing, telemetry. These are the major elements of a launch facility. Starting at T-2 days, we're going to see how these facilities are used to launch one type of payload, in this case, a grenade experiment. The assembly and the initial checks on the payload may take up to 1.5 days. We want to be ready to fire at the selected time. At about T-12 hours, we move the rocket from the storage area to the launcher. Rockets such as this need the proper dollies and handling equipment for convenience and safety. Notice, too, the roadways provided. Handling equipment is available to position the Nike for smooth movement onto the launch rail. At about this time in a remote area, the grenades are being loaded into the plastic nose cone. At altitude, these will be exploded in series to provide successive measurements of the speed of sound and derivation of temperatures. The payload, minus grenades, but mated with the second stage, is fastened to the booster on the launch rail. This should be completed by T-minus 4 hours. About this time, we begin observing the winds and other meteorological parameters to make our first impact prediction. From weather data, we can determine preliminary launcher settings for impact in the desired area. After the nose cone is installed with live grenades, we want the minimum handling of the rocket by the least number of people. Now we begin to keep close track of the time beginning an actual countdown. Range safety information may come from range surveillance aircraft or from surveillance or tracking radar to assure that the range area is clear. In the instrumentation area for this grenade experiment, final equipment checks are made on the sound ranging recorders. The recorders will obtain data from a quiet area nearby, where a series of sound ranging microphones are installed under these covers. A final check of the weather for the wind weighting, a process of assembling data and computing impact areas. Adjustments can be made to the launcher for safe impact, considering the current winds.
In the 11 area, all personnel will take cover and remain under cover until T+2 minutes.
In the instrumentation section, all settings are checked, telemetry and recorder settings. In the control center, range safety is again verified, and timing and instruments are checked following a countdown manual. The project scientist verifies that the experiment is ready and switches instrumentation to internal power in the rocket, transponder to internal power. Recorders are turned on for tracking and telemetry. Sound ranging recorders on.
20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, mark.
From this tracking recorder, we get information as to the range and direction of the payload at the time of each grenade explosion. We are about to see the time of arrival of the sound waves at each of the sound ranging microphones. When this data has been reduced and analyzed, it will tell us the temperatures and winds to altitudes of almost 100 kilometers. For different rockets, for different experiments, for different nations, procedures may vary Facilities may vary. Rocket ranges need not be complex. Recently, one nation set up a range for $250,000. Depending on the experiment, low-cost rockets may be fired from simple ranges so that many countries can do substantial research for the advancement of scientific knowledge in all nations.